Moving along to the second question that we can ask about the span. If you're given a set of vectors, you can ask, what is the span of this collection? And so, if it could be the case that the span of S is all of V. This is equivalent to the idea that any element of V can be written as a linear combination of elements of S. So in some sense, S is a sufficient toolkit to be able to build anything. And that means that an equation like C1V1 plus da 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 up to CK equals B can always be solved, or in other words, that it has a solution for any vector B. So earlier we were looking at a particular given B. Now we're like, well, can you solve this for any B? So sometimes you can, sometimes you can't. If the span of S is not equal to V, it may be the case that that span S doesn't have much of a useful description. But in the case where we're in Rn, we can say a little bit. So, for example, if we're looking at just a single element set. So if S just has one vector, actually here let's stick with calling them V's. So I'll call this guy V1. So if S is just a single vector, then the span of S, well, okay, so all linear combinations of a single element, that amounts to the same thing as all scalar multiples of just one thing, because 1V plus 2V is the same thing as 3V, which is just like scalar multiplying the original V by 3, right? So then span S is going to be a line, except for the exceptional case in which you are unlucky enough to have the zero element as your thing, in which case, in that case, then the span of zero is just the trivial vector space consisting of the single zero vector. Now, what if you had more than just one thing? So if S is V1 and V2, then the span of S could be a plane. And in fact, it will be a plane unless X and Y lie on the same line. So it'll be a line if and only if Y is a constant multiple of X or X is a constant multiple of Y. Okay, and then notice that if this happens, so if Y is a scalar multiple of X like this, then that's exactly the situation where Y is an element of the span. Oh, why am I calling these X and Y? I'm sorry. Let me back up. I forgot I changed notation. It's a line if and only if V2 is equal to C times V1. And that's exactly the same thing as saying that V2 is in the span of V1. So the idea is that if V2 is not in span V1, then by adding it, the span of v1 and v2 will be bigger. But if v2 were already in the span, then when you add it, you don't get anything bigger. Maybe that sounds trivial to say, but I just wanted to make a point of it. So if, oh, and I'm off track here. So if, say, S is v1, v2, v3, so we have 3 elements now, then it could be that span S is a 3 space. So by a 3 space, well, technically a hyperplane of degree 3, I mean like a copy of R3 that lives in whatever vector space you're looking at, R5 or something, who knows. So a 3-dimensional subspace. But if your new element happens to be some linear combination of v1 and v2, then the span is just going to be a plane again. And so notice that this is the case where v3 is now in the span of v1 and v2. So the picture that goes with this is like if we have, say here's v1 and here's v2, right? So then the span of them is all the places I can get to by adding these vectors together. So by tacking on a v1, I could get out to this point over here, and so on and so forth. So I end up basically looking at this kind of grid of places that I can get to with multiples of, adding multiples of these vectors together, and I get this whole plane. Eventually, I can get to all these places. Now, if I add a third vector, if that vector is, say this one here, v1 plus v2, then I don't get anywhere new. Adding this onto anything that I had before just gets me to other places still in the same plane. But if I add on some new vector that's going up into space, now I can start getting all over the place. And it ends up that the span of these, the 2 black vectors and the purple one together, that will be all of R3.